For our Embedded System Design project, Fall 2017, we recreated a classic arcade game based on the movie Tron. We used two rovers, one autonomous and one user-controlled, to help to emulate the style of the arcade game.
Hi, my name is Beijun Liu, and in our project, I work on the Wi-Fi on the rover, GUI, and server on Raspberry Pi.
Hi, my name is Peter Singalis, and for our project, I worked on riverside communications and sensors.
Hi, I'm Frank Liang. In our project, I work on the motor thread.
Hello, my name is Hao Gu. I worked on AI algorithm for our project.
The rule of this game is simple. Two battle tanks are aimed to destroy each other. For example, the blue tank is now trying to destroy the yellow tank. In our project design, we have two rovers representing two battle tanks. One rover represents the hacker, which is artificial intelligence rover. The other one is the guard, which is user-controlled rover. Both rovers will leave an unerasable past. It's not visible on the arena, but visible on graphic user interface of Raspberry Pi. If one rover touches the path created by the other rover, the path created by itself, or the wall of the arena, it will be destroyed.
Our arena is built on a collection of gray puzzle mats, and we tape it with white tapes to simulate the grid system. This is a 4x6 grid system. The top left corner on the arena has coordinate 0, 0, and the bottom right has 5, 3. Two rovers can start at any intersections on the map, at any directions, but the player needs to enter the coordinates in the direction for both rovers manually to the GUI. The graphic user interface of our system consists of two sections, the map visualization and the control panel. The map area simulates the game that is playing on the physical arena, while the two rovers will not have the classic Tron traces at the back. On the actual arena, the map on GUI will show the traces in different colors to tell the AI rover and the user rover. For the control panel, it records the coordinates and directions of both rovers and sends them to the server controller using Qt signal and slots. The start button sends a signal to tell two rovers on the physical arena to start playing. After the game starts, player can control the user rover to change directions using the up, down, left, and right buttons that is provided on the control panel. This is our demo video. On the right and up corner of the screen is our GUI application. Before playing, there are 4 things that the user needs to tell the system: the coordinates and directions for both rovers. The AI rover is in the up and left corner of the arena, so it's in 0, 0, and the direction is to the right. The user rover is in bottom right corner of the arena, so it's in 5, 3, and the direction is up. After entering the initial information, the player hits start. After the game starts, both rovers start moving immediately. The green and red light show the AI and the user rover respectively. The user rover keeps going straight if the player doesn't click on the control panel. The AI rover changes its direction intelligently based on the routes that the two rover covers. As you can see, when the player clicks on the turning buttons, the user turns to either left or right when it reaches the next intersection. The AI rover has no ways to go. In this case, user wins. This is another demo of our video.
For our project, we outlined a number of requirements at the start of the semester. We specified 3 different types of requirements. First, physical requirements that describe how the rovers must move in the gameplay area. Second, communication requirements that describe how the server must communicate with our rovers. And finally, rover requirements that describe how the rovers must communicate with our Raspberry Pi server. For physical requirements, we specified that the rovers must successfully be able to play the Tron light bike game. This means that they must be able to drive around the playing field using commands that are provided to them by the server. We also specified some margin requirements, such as error for the rover line following. The physical requirements can mostly be seen in our demo video, where our rovers are exercised in many different scenarios. For our communication requirements, we specified that the Raspberry Pi server must communicate with the rovers on a two-way connection, both sending and receiving data. We said that the server must communicate to the user rover by sending data across a wireless connection based upon the user's input to the GUI. We also specified that the server must simultaneously communicate with the AI rover by sending data based on the instructions provided by our AI algorithm. Finally, the Raspberry Pi must be able to receive location updates from the rovers so it can update the GUI. We met these requirements by implementing server-side Python sockets, bound to 2 different ports while using multi-threaded approach to designing the GUI in order to handle both rovers. For our rover requirements, we specified that the rovers must communicate their location to the server upon encountering a joint in the playing field or a place where 2 lines of tape cross. We specified the rovers also must be able to receive commands from the server instructing the rovers where to go. We met these requirements by implementing ISR-driven UART communication to the rover side that allowed us to send and receive data in a byte-by-byte fashion in communication with the server.
The AI rover uses a combination of algorithms in order to intelligently navigate around the play game area. The 2 main algorithms that play the essential roles in predicting the best move are flood field and minimax. Flood field helps to visualize the minimum steps that the rover on a certain position on the map needs to travel to an arbitrary point. The algorithm recursively fills up the map by filling incrementing numbers from a certain point to the boundary of the map based on the steps that a point needs to reach another. The matrix retrieved from this depth-first algorithm helps the evaluation of which direction provides the highest probability of winning the game. The image below indicates roughly how the algorithm works. X is the center position we try to evaluate, and the numbers around it are the smallest numbers to travel to that point. Minimax is an algorithm that helps to determine the space a rover will reach earlier than the other rover. The image below shows how the algorithm works. Blue and red regions on the map indicates the space where blue and red rover can reach before the other one. When the 2 rovers, blue and red, start moving, you can see the region covered by the changes. My goal is to use the flood field algorithm to find the size of such regions and calculate the region volume for each of the 3 moves, straight, left, and right. The next move will be determined by the direction that leads to the biggest region covered on the map.
Okay, so now let's talk about the robustness of our project. Initially, we use sonar sensor to detect the wall. However, it's highly unreliable. The rate of success is only about 50%. We figured it's not a problem in our code, but in the hardware itself, because if we hold sensor tightly, it will work with no problem. This sensor has no impact on our design of project, so eventually we take the sensor out. We have tested our rover in different environments. Light, battery, or texture have no impact on our rover. The only exception is that the grid needs to be clean. This is because in order to make the line following sensor work well, the grid needs to have high contrast to the mat. So we have to clean the arena using the wet wipe before we start.
In terms of reliability, our code is pretty good. On the rover side, the state machines that are implemented can run forever with no issues. However, when it comes to connecting the rovers to the server, occasionally we run into some issues that require either a server or rover reset. On the server side, occasional unhandled exceptions cause the program to crash, but in most cases, the server executes without flaw. Overall, even with these small occasional issues, the project works well and allows the Tron Lightback game to be played well enough that someone familiar with Tron could recognize it.
So speaking of the improvements we could make for this project, at the end of the semester we found the following 4 aspects we could do better if you have more time. First of all, for the server, we could add more error handlings in order to catch the errors without crashing the whole application. Or also, after we got a winner, we should have some leaderboard to make the game look more competitive. If we have time, we will also add the reset button so we don't have to restart our application every time we want to replay the game. So the AI algorithm is not ideal when the 2 rovers get close to each other. We could also set up difficulty levels for the game to have more fun. Third, our project can also add some more sensors. For example, we could add a sonar sensor and add walls to our arena so we can prevent the rover run out of the arena. Our rover has hardware limitations. For example, in order to make the rover move, the duty cycles has to be roughly larger than 45%. If we can lower this threshold duty cycle to 20%, we will have smaller turning angle and it will make the rover turning more smoothly.
Finally, we would like to thank Dr. Plasman as well as the TAs Chang and Matt for their support this semester.